about the online that the offline doesn't have is that, like this question here, there is an actual video of me explaining the answer to that very question. So you do a question, you click feedback, and it has a video of me answering that question. That's something that we weren't able to offer on the USB in the same way. On the offline version, it's just one long video with a bunch of explanations, but it doesn't trigger inside of the custom feedback. It's only digital custom feedback on the offline version because of the limitations. Either way you go, I'm here to help you any way that I can. My bargain is that these videos will help add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 8.1 in our video series. We're going to be in Article 240, and we're going to be learning all about overcurrent protective devices. You'll hear me use the term OCPD throughout the rest of the program, and all it stands for is overcurrent protective devices. But to simplify it even further, just think about it like this. Anytime you see OCPD, it just means breakers and fuses. Whether it's the individual breaker at a branch circuit, 20 amp, or it's a 100 amp feeder breaker, or our main 200 amp disconnect. It's either going to be a breaker or fuse, and they're all OCPD. Let's get to it. Table 240.6a is one of my favorite tables in the NEC. It's where we get our standard ampere ratings from. And although it seems like the least of all the tables, it's very powerful throughout the electrical industry. Anytime we come to a new table, we always read the black bold heading to make sure that we're in the right table. Standard ampere ratings for breakers and fuses. Starting on the left-hand side is where it starts with our numbers. You should pull your codebook out and look at it now. If you're in the 2023 and later, it's going to start with 10 amps and go up. And in the 2020 and previous, it's going to start with 15 amps and go up. And then it goes up by fives, 15, 20, 25, 30, 35, 40, 45, 50. And when we get to 50, it starts jumping by tens and even larger numbers as we move up in amperage. The reason that this table is so important is it unifies the entire electrical industry. The manufacturers make these size breakers. The stores stock these size breakers. Installers purchase these size breakers, and when we are doing our load calculations in the NEC, these are the sizes that we're actually going to use. We're going to learn all about it in this lesson. Table 240.6a, standard ampere ratings for breakers and fuses. Let's get to it. Let's look at the major points for general overcurrent protective devices. I say general for a reason, because there are other parts of the code that modify, change, or erase the things that I'm getting ready to teach you. A good example is when we get to motor overload devices. But these rules that we're getting ready to learn apply blanket across the NEC unless another section tells you otherwise. The first one is the next size up rule. And that's the next standard size on that table that we just learned about. Let's imagine that we have a 59 amp known load. And for the rest of the program, I'm going to call it known load. And there's a reason that you'll learn about here in a minute. But do they make a 59 amp breaker? They don't, do they? What we would do is we would go to our table, 240.6a, and we're going to look at the next standard size. So we go 15, 20, 30, and then we look here and we see 50. And then in between 50, there's no 55, and it jumps to 60. If we have a 59 amp load, we're going to choose a 60 amp overcurrent protective device. Now, that may not feel good at first when you first start wiring and learning this stuff, but later we'll understand that there are rules in place when we get to sizing our wire that are going to make it so everything's okay and we're totally protected. The next major point is going to be continuous loads at 125%. There are two different names that you may see, continuous load or continuous duty. A continuous load is defined as expected to run for 3 or more hours at full current. And in the exam prep world, it's going to look like this. You have a load that's known to run for 5 hours, what would the blah, 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 and it'll ask you for wire size or breaker size. Or it might say 5 hours or 10 hours. It doesn't matter how many hours it is. If it's 3 or more, it's considered a continuous load. You may also hear the word indefinitely. Just to try to throw you off, they might use the term indefinitely. Well, it falls under the same classification of needing a 125% multiplier. Remember, it's just another demand factor. Let's do an example. Let's take our 59 amp known load from before, and let's imagine that it was told to us that it's a 59 amp continuous load. What we would do is we would take our 59 amps, multiply it by 1.25, then we have a new known load of 73.75. That old load is gone, the 59 is gone, the 73.75 is our new known load, and that's what we would go size our breaker and subsequently our wire by. How we would do that is head to table 240.6a. We're going to look at the next standard size, so we're above 70 and it jumps to 80, and we would put this on an 80 amp overcurrent protective device. Our final major point is going to be that the overcurrent protective device equals the service size. Let me explain what I mean. Let's imagine that we did a whole house load calculation and it equaled 180 amps. Well, now we have to size the main breaker for that house, don't we? For that, we're going to head to table 240.6a and we're going to choose the next standard size. We put it on a 200 and we're done. But the question is what size is the service? Is it based off like the rating of the equipment bus? Maybe it's a 225 rated. No, it's actually based off the size of the main breaker or main fuse for that structure. So this would in fact be a 200 amp service. The load calculation dictated what size breaker we used, and the breaker size that we used dictated the size of the service. And this is very important as we get farther into the program. That's it for lesson 8.1. You can head over to electricalexamcoach.com to unlock the practice quizzes and everything in the ECC Testing Center. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 8.2 in our video series. And in this lesson, we're going to learn how to size overcurrent protective devices for non-continuous and continuous loads. Let's get to it. What size breaker would you use if you had a 56 amp load on a piece of equipment? Step 1, find the total connected load. The known load as of right now is 56 amps. Now we check for demand factors. In this case, it doesn't mention that it's a continuous load or it's running for any specific amount of time. It also doesn't call out a specific type of equipment, like a motor or air conditioner compressor, that might lead us to other sections of the code. Therefore, there are no demand factors. We head over to table 240.6a and we select the next size up. In this case, we have a 56 amp load, which would lead us to select a 60 amp overcurrent device. Great job. What size breaker would you use if you had a 34 amp load on a piece of equipment? Step 1, find the total connected load. The known load as of right now is 34 amps. But we gotta check for demand factors. There are no continuous loads, and there are also no specific pieces of equipment. So therefore, there are no demand factors. We're gonna head to our table, 240.6a, and we're gonna choose the next size up, which in this case would be a 35 amp breaker. And that's where I want to take the time right now to point out that you should always go to the table and verify the size that you should choose. This is where you can let field experience burn you when you're in the testing center. Because if we're out in the field and we see a 34 amp load, we might put that on a 40 amp breaker. So you might see 34 amp load inside the testing center and automatically assume that the next size up is 40. But you have to go by the values in the table. The correct answer in the field and in the testing center in this case would be a 35 amp breaker. Let's get to it. What size breaker would you use if you had a 40 amp load on a piece of equipment? Step 1, find the total connected load. The known load right now is 40 amps, but we check for demand factors. And in this case, there are no continuous loads or specific piece of equipment. Therefore, there are no demand factors. We're going to head to table 240.6a. Even though we feel confident that it's a 40, I want you to always be in the practice of flipping to the table and verifying that you have the correct size breaker. And in this case, we land right on a standard size, so we're going to select 40. And we select D. Great job. What size breaker would you use if you had a 26 amp load in a house and it's known that it will run for 4 hours at a time at full current? Step 1, find the total connected load. Our known load as of right now is 26 amps. Now we got to check for demand factors. In this case, it's going to qualify as a continuous load. Any load that's expected to run for 3 or more hours at its full current must have that 125% continuous load multiplier. So we take our known load multiplied by 1.25. That gives us a new known load of 32.5. In that case, we would round up to 33, and that's our new known load. Then we head to table 240.6a, and we choose the next size up. And in this case, it's going to be a 35 amp breaker. Great job. What size breaker would you use if you had a 40 amp load in a house and it's known that it will run for more than 5 hours at a time? Step 1, find our total connected load. Our known load as of right now is 40 amps. But we must check for demand factors. And in this case, we have our continuous load multiplier. It's very important to note that the test makers will put different numbers of hours to see if you're paying attention. They'll put, what if the load runs for 16 hours or 20 hours? If it's anything 3 hours or more, it's going to have that 125%. We take our known load multiplied by 1.25, and that gives us a 50 amp new known load. We head to table 240.6a, and we're going to land directly on a standard size breaker, which is a 50. So we come back and select A. Let's get to it. What size breaker would you use if you had a 47 amp load and it was expected to run indefinitely? Step 1, find the total connected load. Our starting known load is 47 amps. Now we check for demand factors. And in this case, it gets that 125% continuous duty, just like a continuous load. We take our starting known load, multiplied by 1.25, and that equals 58.75. And in this case, we would round up. So 59 is our new known load. Now let's head to table 240.6a. And in this case, we're going to select the next size up, which happens to be a 60. Great job. That's the end of lesson 8.2. And I want to take this moment and encourage you and let you know that you're doing a great job and keep up the hard work. And just don't forget the reasons that you're doing this. For your family, for your career, for taking your family from where you guys were to where you guys are going. Because it's easy when we get exhausted and it's hard and we're on our way to that next level to forget all the reasons that we're doing this in the first place. I want to let you know that I'm here for you. Anything that you need, you can always just email me at electricalcodecoach@gmail.com. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 8.3 in our video series. We're still in Article 240, but we're going to be doing sample calculations of whole homes and businesses and selecting the main overcurrent device. Learning how to take all the work that we've done in the program up until this point, the load calculations and everything, and then take those total VAs and find out how to choose that overcurrent device, which will ultimately dictate the size of the service. Let's get to it. What size main breaker would you select for a home with a total calculated load of 23,123 VAs on a 120 240 volt system? Step 1, find our total connected load. Well, they've already done the load calculation for us, so all we have to do is take our total known VAs and divide it, and that's going to give us our load in amps. And in this case, it's 96.35. We would round down to 96. Now we check for demand factors. Because this load calculation was already performed, there are no more demand factors to do. They were done along the way, right? We would have performed our range demand factor, our dryer demand factor, and then now we have this total lump sum of 23,123. So all we have to do is divide by 240, and there are no demand factors. Now that we have our known load, we head to table 240.6a, and we choose the next size up. And in this case is going to be a 100. Great job. What size main breaker would you select for a home with a total calculated load of 47,000 VAs on a 120 240 volt system? Step 1, find our total connected load. In this case, they've done all the math for us, and 47,000 are our total VAs. All we have to do is divide that by the system voltage. And in this case, it equals 195.83, and we would round down. Now we check for demand factors. And in this case, there are no demand factors because they were already performed to get us that 47,000 value. Now we head to table 240.6a and choose our next standard size. And in this case, it ends up being a 200 amp breaker. Great job. What size main breaker would you select for a home with a total calculated load of 38,000 VAs on a 120 240 volt system? Step 1, find our total connected load. They've already done the math for us, so all we have to do is divide by the system voltage. And in this case, it equals 158. Now we check for demand factors. And like we said before, there are no more demand factors on this calculation. We head over to table 240.6a, and we choose the next standard size breaker. And in this case, it's 175 amps. What size main breaker would you select for a business with a total calculated load of 95,000 VAs on a 140 240 volt system? Step 1, find our total connected load. They've already performed the load calculation for us, so all we have to do is divide by the system voltage. And we end up with 395.83, and we would round up to 396. Now we check for demand factors. And whether it's a home or a business, all the demand factors were already performed to get that original 95,000 number. So there are no more demand factors. Now we head to table 240.6a and we choose the next standard size breaker. And this would be a 400 amp breaker. This would also be a 400 amp service. Let's get to it. Now let's do that exact same calculation but on a three-phase system and show you the beauty of three-phase. What size main breaker would you select for a business with a total calculated load of 95,000 VAs on a 120 208 three-phase system? Step 1, find our total connected load. Well, they've already given us our total VAs, so all we have to do is divide. But with three-phase, there's one extra step. Because of the geometric nature of three-phase, we have to take that 208 and multiply it by the square root of 3. The square root of 3 just so happens to be 1.732. Once we work that math out, we end up with 360.256. And it seems like a lot of work on the front end, but you'll find out that you'll trade this little bit of math for what this is getting ready to provide for us. Now we can take and do our math, and after we divide it out, we end up with 263, and of course we would round up in this case. There are no more demand factors, so we head to table 240.6a and choose the next standard size. And this is where the beauty happens. We're going to now put this on a 300 amp breaker instead of, like in the previous question, it would be on a 400 amp, meaning that we'd have to have larger wire in the previous question, which may lead us to have larger pipe, which we may end up with a larger cost of overall project. The beauty of three-phase is the numbers come down. So this one's on a 300 amp service, which means we can put it in smaller pipe, which might end up having a smaller overall cost. Let's get to it. What size main breaker would you select for a business with a total calculated load of 80,000 VAs on a 120 208 three-phase system? Step 1, find our total connected load. In this case, they've done the work for us. They've given us the 80,000. Now all we have to do is divide. We do our little bit of pre-work and we end up with 360. Now we take and divide that out and we end up with 222 amps. In this case, we'll round down to 222. There are no more demand factors in this calculation. We head over to table 240.6a, choose the next standard size up, and put this on a 225 amp service. That's the end of lesson 8.3. You can head over to electricalexamcoach.com. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And this is lesson 9.1 in our video series. We're going to be in Article 310, and we're going to be learning all about ampacity. Ampacity is the maximum current measured in amperes that a conductor can continuously carry under its usage conditions without exceeding its rated temperature. Everything that we're doing in this program and out in the electrical field is to protect first the people and then the equipment. And it's no different with the wire. This wire is only rated to handle so many amps before the insulation will start to deteriorate, and ultimately we could end up with a fault, short circuit, or just arcing and sparking. With that being said, in this video series, we're going to slow down and we're going to master wire ampacity and how many amps a wire can hold and how to select the right wire for the right load. Let's get to it. Now let's learn about our primary ampacity table. If you're in the 2017, it's table 310.15B16. And in the 2020 and later, it's table 310.16. Same information, new name. If you're in a softbound NEC, these should be your page numbers, depending on what print of the NEC you have, whether you got the first round or get you close enough. The most important thing is read the title of the table and make sure that it matches the actual table number. Let's get to it. Now, there's a lot going on in this table. We're going to slow down in this lesson. This is our ampacity basics lesson. Because if you don't get this, it's going to be hard to have an electrical career. It's going to be hard to ever be able to pass your examination. So we're not in any hurry. If you need to watch this video over and over, you can do it. The first distinction we want to make with this table is that it's actually two tables. On the left-hand side is going to be for copper conductors, and on the right-hand side is going to be for our aluminum and copper-clad conductors. Left-hand side copper, right-hand side aluminum. And if you'll notice, they mirror each other, but in the NEC, it's smushed all into one table. Now let's take a look at what all this information means. Now we're going to do a quick breakdown of the table. We won't stop on any specific part until we need it in the program because I don't want to confuse you. And later you'll understand why I did it piece by piece. But we read all of our tables from top to bottom, left to right. I want you to focus on the left-hand side because that's the copper side, but you'll notice that everything that we do is going to be mirrored over on the aluminum side. So starting at the top, it gives us the scope of the table. We're not going to get into that right now. It comes later in the series. Then you'll notice there's a 60, 75, and 90 degree C columns. Below that are going to be the insulation types like THHN, THWN. On the left-hand side, you're going to have the conductor sizes column. Now let's take these piece by piece and explain exactly how to use them. Now let's learn about terminals and insulation rating. And that's where these 60, 75, and 90 degree C columns come into play. Whether we're dealing with terminals or insulation around the wire, each one of them can only handle so much heat safely. Whether it's a lug or a breaker or a switch or the insulation around the wire, they're all rated for specific temperatures. I'll give you a little heads up. Out in the field, all of these are almost 99% of the time rated for 75 degrees C. And ratings. Some of them are rated for 60, some of them are rated for 75, and some of them are rated for 90. The reason this is important is it's going to help us choose which one of these columns we select our ampacity from. If the terminals are rated 75 degrees, we're going to choose the 75 degree C column most of the time. I'll explain what most of the time means later in the program, because this section is just like other sections of the NEC. There are blanket rules that apply generally, but later what I want you to remember is we're going to match the column that we used based off the terminals that the device is rated by. Regardless of what the insulation is, we can choose from whatever column that the terminals are rated by, unless modified by another code. Now let's lay some ampacity ground rules. Unless modified by a specific piece of equipment or another code, these rules will apply generally. If the question states that it terminates to 60, 75, or 90 degree C terminal lugs, you're going to make your selection from that respective column. And as with overcurrent protection, we're going to do 125% demand factor for all loads that are expected to run for 3 or more hours. Remember our continuous load rule? That carries over into wire sizing as well. Let's get to it. What size AWG copper conductor would you select for a 60 amp load using THHW terminating on 75°C terminals? Step 1, find the total connected load. Well, in this case, we already have the load. It's 60 amps, but we must check for demand factors. They've not told us about a specific piece of equipment or that it's a continuous load, so there are no demand factors. But we have to learn one important rule for sizing wire. The wire must meet or exceed the known load. There is no next size up rule. The wire always has to meet or exceed the known load. So we head to our primary ampacity table, and we're going to start on the left-hand side because our question is copper. Always carefully go through these steps. What type of metal? Copper. What are my terminal ratings? They are 75°C. What is my known load? 60. I'm going to start down the 75°C column until I find a wire that covers the known load, and then I'm going to use a straight edge to come over and select my size wire. And in this case, you would put it on a 6-gauge wire. We go back and we select B. Great job. What size AWG copper conductor would you select for a 74 amp load using THHW terminating on 75°C terminals? Step 1, find the total connected load. It's 74 amps. Now let's check for demand factors. Well, in this case, there's no specific pieces of equipment and there's no continuous load, so there are no demand factors. And we have to remember that our wire must meet or exceed the known load. We head to our primary ampacity table. We make sure that we're on the right side of the table. In this case, it's copper. And we have 75°C terminals. So now we take off and find a wire that will cover the known load. We find one that will cover 74 amps. We use a straight edge to come over and tee off at number 4. And we're going to select A. Great job. That's the end of lesson 9.1. You can head over to electricalexamcoach.com for quizzes that go along with these videos and unlimited access to the testing center. Ampacity is one of those topics that you have to take one bite at a time. So don't get overwhelmed. Take your time. I know that you can do it. I am the Electrical Code Coach, and my bargain is that these videos will add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And this is lesson 9.2 in our video series. In this lesson, we're going to be sizing wire for continuous and non-continuous loads. Let's recap on the basics before we get started. If the question states that it terminates to 60, 75, or 90°C terminals, we're going to make our selection from that respective column under normal circumstances. And the second one is, as with overcurrent protection, like we learned before, we're going to do 125% demand factor for all loads that are expected to run for 3 or more hours. Let's get to it. What size copper conductor would you select for a 40 amp load using THHW terminating on 75°C terminals? Step 1, find the total connected load. In this case, we know the load, it's 40 amps, but we must check for demand factors. It doesn't mention a specific type of equipment or that it's going to be a continuous load, so in this case, there are no demand factors. And we always have to remember that all wire must meet or exceed the known load. So we have to find a wire that meets or exceeds 40 amps. We head to our primary ampacity table, and the first thing we're going to do is check the type of conductor. It's copper, so we're going to start on the left-hand side of the table. We're in the 75°C column because that's our terminal rating. Then we're going to slide down and find a wire that meets or exceeds the known load, and we find out that it's an 8-gauge conductor. And we select C. Great job. What size copper conductor would you select for a 60 amp load running for more than 5 hours using THHN type wire terminating on 75°C terminals? Step 1, find the total connected load. Well, our starting known load is going to be 60 amps, but we must check for demand factors. When we find out that it's going to be a continuous load, we need to remember to do our 125% rule for continuous loads. So we take our original known load multiply it by 1.25, and that gives us a new known load of 75 amps to size our wire by. And remember, our wire must meet or exceed the known load. We head to our primary ampacity table. We head to the copper side because it wants copper conductors. We're in the 75 degree C column, and we need to go down and find a wire that meets or exceeds 75 amps, and we find that it happens to be a number 4. Let's get to it. What size copper conductors would you select for a 40 amp load that's considered a continuous load, using THHN type wire terminating on 75 degree C terminals? Step 1, find the total connected load. In this case, our starting known load is 40 amps. Well, we have to check for demand factors, but they've already let us know that it's going to be considered a continuous load. We take our original known load, multiply it by 1.25, and that gives us a new known load of 50 amps. And all of our wire must meet or exceed the known load. We head over to our primary ampacity table. We're going to start on the left-hand side because they want copper conductors, and we're in the 75 degree C column. We come down and we find a wire that meets or exceeds our load, and we're going to put it on a number 8. Great job! What size aluminum conductors would you select for a 90 amp load running for more than 5 hours using THHN type wire terminating on 75 degree C terminals? Step 1, find the total connected load. Well, our starting known load is going to be 90 amps, but we must check for demand factors. In this case, we find out it's a continuous load. We're going to do our continuous load math. We take our starting known load multiplied by 1.25, and that's going to give us a new known load of 112.5 amps. Now, we have to remember that all of our wire must meet or exceed the known load. We head to our primary ampacity table, but this time we have to be careful because they are wanting aluminum conductors. So we're actually going to start on the right-hand side of this table. We're going to start on the right-hand side. We're in the 75 degree C column. We come down and we find a wire that meets or exceeds the known load, and we find out that it needs to be on a 1/0. Let's get to it. That's the end of lesson 9.2. You can head over to electricalexamcoach.com to get the quizzes that go along with these videos and unlimited access to our testing center. I am the Electrical Code Coach, and I want you to know that you're doing a great job. If you need anything from me, you can always just email me at electricalcodecoach@gmail.com. Don't give up. I know you can do it. Keep grinding. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 9.3 in our video series. In this lesson, we're going to be sizing the overcurrent protective device and the wire in the same question for all of these loads, for continuous and non-continuous. Let's recap very quickly. If the question states that it's terminating to 60, 75, or 90 degree C terminal lugs, you're going to make your selection from that respective column under normal circumstances. With both OCPD and wire sizing, we still have that 125% demand factor for all loads that are expected to run for 3 or more hours. And we will always select the overcurrent protective device first, and then we'll choose our wire size. And it'll make more sense why we do that once we start sizing services in the next lesson. And once we get into larger amperage questions like 1,000 amps or greater, which we'll learn in the lesson after that one. Let's get to it. What size copper conductors and overcurrent protection would you select for a 54 amp load using THHN type wire terminating to 75 degree C terminals? Step 1, we're going to find our total connected load. In this case, we have it. It's 54 amps. But we must check for demand factors. Well, they've not mentioned a specific piece of equipment or that it's going to run for 3 or more hours. So in this case, there are no demand factors. Now, what we're going to do is size our overcurrent protective device first. You always size that first. So we head to our overcurrent protective device table, which is 240.6a for a 54 amp load. We're going to go down and choose the next standard size up. In this case, it's going to be a 60. Now, let's head and size the wire. For that, we're going to head to our primary ampacity table. We're going to start on the left-hand side and make sure that we're on the copper side because our question asks for copper. And we're in the 75 degree C column in this case. We're going to slide down and find a wire that covers the known load of 54 amps. And we're going to select a 6 gauge wire on a 60 amp overcurrent device. Let's get to it. What size copper conductor and overcurrent protection would you select for a 62 amp load using THHN wire terminating to 75 degree C terminals? Step 1, find our total connected load. In this case, it starts at 62 amps, but we must check for demand factors. With there being no special pieces of equipment mentioned or the fact that it's running for 3 or more hours, in this case, there are no demand factors. Now, we go ahead and size our overcurrent protective device. We head to our table with a 62 amp known load, and we're going to choose the next size up, which puts it on a 70. Now, we can size our wire. For that, we're going to head to our primary ampacity table. We're going to be sure to start on the copper side because it's asking for copper. We're in the 75 degree C column. We slide down and find a wire that can cover the known load, and we find out that we're going to have a 6 gauge wire on a 70 amp breaker. Let's get to it. What size copper conductors and overcurrent protection would you select for a 105 amp load using THHN type wire terminating to 75 degree C terminals? Step 1, we're going to find the total connected load. Our starting known load is 105 amps, but we must check for demand factors. It doesn't mention a specific type of equipment or for how many hours that it's running, so in this case, there are no demand factors. First thing we're going to do is size our overcurrent protective device. For that, we head to table 240.6a and choose the next standard size up. And this is why it's very important for you to always go to the table and not just go off of memory or what you might do out in the field. Because out in the field, you might say, oh, this needs to be on a 125 because 125 is a common number. But how many of you know that there's actually a 110 amp breaker in between 100 and 125? I've seen them, I've worked with them out in the field, but they're not very common. Usually out in the field, we'll jump from a 100 to a 125 for like sub-panel sizing. But you have to be careful here. Always go to the table because the correct answer for this question is actually a 110 amp breaker. Now, let's size the wire. For that, we head to our primary ampacity table. The known load's 105 amps. We're on the copper side of the table because that's what the question said. We're in the 75 degree C column, and we go down and find a wire that covers the known load, 105 amps, and we're going to end up with a number 2 wire on a 110 amp breaker. Great job. What size copper conductors and overcurrent protection would you select for a 105 amp load expected to run for 3 or more hours using THHN type wire terminating to 75 degree C terminals? Step 1, find the total connected load. 105 amps is our starting known load, but we must check for demand factors. When we look, we find that we have the 125% continuous load rule, so we do our math. We take our original starting known load, we multiply it by 1.25. That gives us a new known load of 131 amps. And now we can size our overcurrent protective device. We head to table 240.6a and we choose the next standard size, which is a 150. Now we can come back and size the wire. We head to our ampacity table. We're on the copper side, 75 degree C column. We're going to go down and we're going to find a wire that covers the known load. And we're good to go. We're going to select a 1/0 on 150. Let's get to it. What size copper conductors and overcurrent protection would you select for a 50 amp load expected to run for 3 or more hours using THHN type wire terminating to 75 degree C terminals? Step 1, we're going to find the total connected load. Our starting known load is 50 amps, but we must check for demand factors. We see that it's a continuous load, so we're going to have our 125% rule. We take our starting known load, multiply it by 1.25, and that gives us a new known load of 62.5. Now we can size our overcurrent protective device. We head to our table, we choose the next standard size, which in this case is going to be a 70. Now let's size our wire. Heading to our primary ampacity table, we're going to be on the copper side of the table in the 75 degree C column, and we find a wire that meets or exceeds the known load. When we do, we find that it needs to be a 6 gauge wire on a 70 amp breaker. Great job. This is end of lesson 9.3. You can head over to electricalexamcoach.com to check out our pro version. I am the electrical code coach. Value to you, and you will in turn go out and add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 9.4 in our video series. And in this lesson, we're going to be sizing the overcurrent protective devices and wire for commercial and dwelling unit services and feeders. We're actually going to start with commercial because it's easier, believe it or not. Always remember that we're going to select our overcurrent protective device first, and then choose our wire size. Also, the overcurrent protective device size is the size of the service. If we're sizing services and we select a 200 amp overcurrent protective device, whether it's a breaker or fuse, based off the size of the load, and we go to the next size up and it ends up being a 200, that means we have a 200 amp service. And it's very important for us to understand that before we move on in the program, that if I'm sizing services and I end up with a 200 amp overcurrent protective device, and that is the main breaker on that service, that is now a 200 amp service. Let's get to it. What size main breaker and copper conductors would you select for a business with a total calculated load of 80,000 VAs on a 120/208 three-phase system on 75 degree C terminals? Step 1, find our total connected load. In this case, they've already given us the 80,000 VAs, but we have to do that little bit of pre-work first on all of our three-phase calculations like we learned before. We take 1.732, we multiply it by our system voltage, which is 208, and that gives us that 360 value. Now we can divide just like normal. We take the 80,000 VAs, divide it by the 360, and that gives us a 222 amp known load by which we can size our breaker and our wire by. But first, we must check for demand factors. In this case, there are no demand factors, so we can size like normal. Let's size our overcurrent protective device first, based off of 222 amps. We head to table 240.6a, and we choose the next standard size. And in this case, it's going to be a 225. Now we can size our wire. We head to our primary ampacity table. We're going to be on the copper side of the table in the 75 degree C column, and we need to go down and find a wire that covers 222 amps. And in this case, we're going to select a 4-aught. When we put it on a 4-aught wire, we're going to select D, and we're all done. That's why we chose to do commercial first, because it's going off of all the things that we previously built in these lessons with no additional rules. In a few moments, we're going to be on residential, and you'll find that there are a couple extra codes that we need to know about. Let's get to it. What size copper wire would you select for a service with a 125 amp main breaker and a total connected load of 118 amps on a commercial building with a 120/208 service on 75 degree C terminals? Step 1, we're going to find our total connected load. In this case, they give it to us. It's 118 amps, but we must check for demand factors. In this case, there are no demand factors, so we're going to carry on. Normally, we would size our overcurrent protective device, but if you notice in the question, they've already done that for us. So all we have to do is size our wire. We're going to head to our primary ampacity table and find a wire that is good for 118 amps. We go down, we slide down the 75 degree C column on the copper side, and we're going to find that we select a number 1. And in the testing center on the Electrical Exam Coach website, you'll have more variants of this and practice of this, but that's how easy it is with commercial. First size the breaker based off the known load, and then you're going to size the wire. It really is that simple. Now let's dive into residential and learn a few more codes. Now let's learn how to size dwelling unit services and feeders in between 1 and 400 amps. This applies to single-family dwelling units and the individual units of two-family and multifamily dwelling units. And it's affectionately called the 83% rule. The next few slides are very dense, so I want you to slow down, take your time, watch it as many times as you need, but I know that you can do it. Keep up the great work. Let's imagine that we have a dwelling, and the first thing we're going to do is find our total connected load. Let's imagine that it's 47,000 VAs on a 240 volt system. That gives us 195.83. We would round up to 196 and go size our main breaker. And the main breaker would be a 200. That's the next standard size. We now have a 200 amp service. Now the next step normally would be to size the wire at 196 amps, right? That's our known load. We can just follow our normal ampacity rules. Well, not with services that are in between 1 and 400 amps. And let me show you what I mean. Let's all head to page 800 if you're in the 17, this table if you're in the 20, and this table if you're in the 2023. This is technically called the 83% rule, but I'm not going to force you to do the longhand math. I'm going to take you to these tables that are in the NEC that are almost like a cheat sheet that makes this super easy to apply and understand. Let's get to it. Once we get to our table, we work all of our tables from top to bottom, left to right, using those headings to navigate the table. On the left-hand side, we're going to find the size of the service and feeder, and this is listed in amps. And you'll notice that it only goes to 400 because the rules that we're learning right now only apply to services and feeders that feed the entire dwelling in between 1 and 400 amps. And I've got a great graphic illustration in the next slide to show you when it does and does not apply. On the next column over, we're going to see the copper side if we decide to use copper, and then aluminum if you decide to use an aluminum. So what you do is size your service. You come down here. Let's imagine it's a 100 amp service and you want to use copper. You slide over and it tells you what size wire to use. It makes it super simple. Now let's put it to practice. Now let's find out when this rule does and does not apply. Let's imagine that we have a single family dwelling. We have the meter socket outside, we have the riser, and we have a back-to-back panel, kind of an old school setup. We have the wire going up the riser and the wire going inside. Technically, this is all service wire all the way to that main breaker, and the 83% rule does apply here, as long as it's in between 1 and 400 amps. Now let's imagine that we have a main breaker outside, we have the service riser, and we have a main sub-panel inside. We have the riser wire and the wire going inside. The 83% rule applies to all this wire. You can apply it to the wire going up the riser, and you can apply it from the meter disconnect combo to the first main sub-panel. Now the rules with this is that it has to be the panel that feeds the entire structure. You're not allowed to use it on other sub-panels or on any sub-panel that does not feed the entire structure. You have to be very careful with that one. So we're allowed to apply it on this one on the left for the whole wire. We go use that table and size our wire based off the table. And the scenario on the right for all of that wire there for the service itself, and then also for the main feeder, as long as that panel that it's feeding is feeding the entire structure. You would go to that table, do your cheat sheet, find your size breaker, slide over, and you'd be able to use that size wire. Let's dive into two-family and multifamily. This is 1 through 400 amps, and this applies to the feeders only. The feeder must feed the entire dwelling. Let's imagine that you have an apartment here on the right-hand side, and it's attached to the larger apartment structure. That's where the main service is. Let's imagine that you have your meter center out here, you have your service riser, and then you have your wire going up. That wire there, the 83% rule does not apply. You're going to use all of the previous rules that we learned before and apply those. But the individual feeder going into that unit does. The 83% rule does apply. And the beauty of this is it allows you to save money in the long run. Whether you're doing single family dwellings only or you're doing the individual units of the apartments, you're going to be able to use a smaller wire based off that table than you would if you went and sized it like normal. And over a year's time, that could save you a lot of money. So that is when the 83% rule does and does not apply. What size copper wire and main breaker would you select for a service with a total calculated load of 47,000 VAs for a single family dwelling on a 120 240 volt system with 75 degree C terminals? Step 1, we're going to find our total connected load. In this case, they've given it to us, but we have to divide to get our amperage. When we do, now we can check for demand factors. And in this case, we do have a demand factor. Is this in between 1 and 400 amps? Yes. Is this on a single family dwelling? Yes. So the 83% rule does apply. So we get to use the table. Step 1, we're going to size our overcurrent protective device. And we're going to head to table 240.6a. We have a 196 amp known load. We're going to choose the next size up and put it on a 200. Now we can use our cheat sheet table. When we head there, we're going to size the wire. Step 1, we're going to be on the left-hand side and find our size breaker. Then we're going to come over to the copper column because that's what it requested, and we're going to find that we need to put it on a 2-aught. And in this case, we would have 2-aught copper on a 200 amp service. Great job. What size aluminum wire and main breaker would you select for a service with a total calculated load of 47,000 VAs for a single-family dwelling on a 120 240 volt system with 75 degree C terminals? Step 1, we're going to find our total connected load. In this case, they've given it to us, and we're just going to divide, just like we did before. Now, we check for demand factors. Is this in between 1 and 400 amps? Yes. Is this on a single-family dwelling or the individual unit of like an apartment? Yes. So, the 83% rule does apply. And we're going to go size our overcurrent protective device. We end up putting it on a 200 amp breaker, just like we did before. But now we have to be careful because the question is asking for aluminum. We head to our cheat sheet table. We start on the left-hand side, and we're going to find our size breaker. Then we have to slide all the way over to the aluminum column, and we're going to find out that it's a 4-aught aluminum. Great job. That's the end of lesson 9.4. When it comes to these type questions, the only way to beat it is through repetition. And the best way to do that is at electricalexamcoach.com. We teach you so much more inside of the quizzes that we don't get the chance to cover inside the videos. There are so many different nuances, different levels, and just topics that we haven't covered on video that we cover inside of those quizzes that are in the testing center at electricalexamcoach.com. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And this is lesson 9.5 in our video series. And in this lesson, we're going to be learning about bundling adjustments and ambient temperature corrections. These are a subset of ampacity. And remember, ampacity is just how many amps the wire can handle safely under its conditions of use without exceeding its temperature rating. Bundling adjustments work like this. When wires are bundled, like in a pipe for example, they have less ability to dissipate the heat, and it reduces how many amps the wire can handle safely. Ambient temperature corrections are like this. If wires are run in an extremely hot ambient temperature, it reduces how many amps the wire can handle safely. We're going to learn about these one at a time. Let's get to it. Let's dive into bundling adjustments. Let's take a look at our primary ampacity table. I want you to turn there now. And these values down below this table are true if, well, the question is if what? If you look at the paragraph above the table, the one that I said we would come back and look at later, it's got some parameters there. It says, hey, these are the ampacities of these conductors if, and the first if that we're going to look at is if there are not more than 3 current carrying conductors inside of a cable, pipe, or even buried in the earth together. Let's take a look at it. Let's imagine that we have a piece of conduit here and we pulled in a black, red, blue, and an equipment grounding conductors. What this table is saying is that those ampacity values listed down below in this table are true as long as you have not more than 3 current carrying conductors in a cable, pipe, or raceway. If you do have more than that, then we have to do what's called a bundling adjustment. Let's learn about our bundling adjustment table. Head to this respective table depending on your code cycle. When we get there, we're going to find that it's very easy to read. Reading all of our tables from top to bottom, left to right, we're going to start here on the left-hand side, and this is our number of current carrying conductors. Let's imagine we have this conduit, and we end up with 6 current carrying conductors. So we're going to slide down until we find our range, and we fall in the 4 to 6 range. Then we need to slide over and find our adjustment factor, which is just another demand factor, which is something you're very familiar with at this point in the program. Let's imagine we have a wire that's 50 amps. We take that 50 amp wire and we multiply it by 0.80, which was our demand factor. And we end up with a wire that is now only good for 40 amps. What they're saying is because the amount of wires inside of this pipe or cable, that the wire cannot dissipate the heat safely. So you have to reduce how many amps the wire can handle. So the new allowable ampacity of this wire is only 40 amps. Up until this point, we've had all hot conductors inside of our conduit. But what happens if we add in a neutral? Is it considered a current carrying conductor? What about grounding conductors? Are they considered current carrying conductors? Well, let's learn how to count conductors now. Now let's learn about current carrying conductor counting, because we're only going to be counting the current carrying conductors. You may get a question on your exam that gives you the number of conductors. That's easy. You're going to go to the tables and do the math. But you may get a question on your exam that asks you, in a scenario of wires, how many of them are current carrying conductors. The first one's easy. All ungrounded conductors. All of the hots are going to be considered current carrying conductors under normal circumstances. The second one is the neutral of a line to neutral load. Meaning if we have a light bulb and it draws 1 amp on a 120 volt circuit, there's going to be 1 amp going in on the hot and there's going to be 1 amp flowing back on the neutral. So it is as well a current carrying conductor. Same thing with a 3-phase 4-wire neutral. We're not going to be dinking around trying to calculate the unbalanced load. We're just going to count it as a current carrying conductor. Then the 3-phase nonlinear neutral load. Nonlinear loads come from large fluorescent lighting or from large computer data centers. You're going to count its neutral as well. Grounding conductors, no, they do not count, and that's one of the easiest ones. You don't have to count those as a current carrying conductor. If we have no adjustment will be made if we have nipples that are 24 inches or less. Let's imagine we have a panel over here on the right-hand side. We put a panel on the left side. We want to run a short nipple that's 24 inches or less. This does not count in our bundling adjustment. Now let's talk about choosing from the right column. And this is the last step before we're actually able to start doing questions. Up until this point, we've always chosen, most of the time, from the 75-degree C column. Now, there'll be times that we choose from the 60, and this is where we start choosing from the 90. 99% of the time, you're going to choose from the 90 anytime that you're doing bundling adjustments or temperature corrections. We're going to choose from that 90-degree C column. We're getting ready to do practice questions, and you'll understand that more fully as we proceed. What is the allowable ampacity of a number 4 copper conductor with 9 current carrying conductors in a piece of 1-inch EMT? Step 1, we're going to verify that our conductors are listed in the 90-degree C column. We head to our primary ampacity table on the copper side, and we make sure that THHN is listed. If it's not listed there, for the purpose of exam prep, I just want you to go to whatever column that it is listed in and do the math. Now, we're going to find our starting ampacity in the 90-degree C column. We head to our primary ampacity table. It's wanting a number 4 conductor, so we start on the left-hand side. We're going to come over and we're going to tee off with the 90-degree C column, and we're going to find out that it is 95 amps. That's our starting ampacity. Now, we must check for demand factors. Are there more than 3 current carrying conductors? There are, so we must apply the demand factor. We're going to head to either table depending on what code cycle you're in. It is our bundling adjustment factor table. And when we get there, we're going to start on the left-hand side. We come down and find our number of current carrying conductors. Then we cross over and find our demand factor. Now we can get to work. We take our starting ampacity, we multiply it by the demand factor, and that gives us a new allowable ampacity of 66.5 amps. A wire that was once good for 95 amps, because of it being bundled in this pipe, is now only good for 66.5, and we select A. Great job! What is the allowable ampacity of a 1-aught XHHW copper conductor with 13 current carrying conductors in a piece of 2-inch RMC? Step 1, we're going to verify that our conductors are listed in the 90-degree C column. When we head there, we find that XHHW is listed. So we're going to find our starting ampacity. We head to our primary ampacity table. We're on the copper side. We start until we find 1-aught on the left. Then we cross all the way over to the 90, and we find that it's 170 amps. Now we check for demand factors. Are there more than 3 current carrying conductors? There are. So we must apply the adjustment factors that are listed in these tables. We go to our adjustment factor table. We're going to start on the left-hand side and find our number of current carrying conductors. Then we cross over and find that it's 50%. We take that and do our math. We take our starting ampacity multiplied by the bundling adjustment factor. Then we're going to have a new reduced ampacity of 85 amps. Great job. What is the allowable ampacity of a number 6 THHN aluminum conductor with 6 current carrying conductors in a piece of 3/4 inch EMT? Step 1, we're going to verify that our conductors are listed in the 90° C column. We head there now, but we're on the aluminum side because the question requested aluminum conductors. And we find that THHN is there, our starting ampacity, in the 90° C column. We head to our primary ampacity table on the aluminum side, and we slide down until we find a number 6. Then we're going to come over and we're going to cross over and find that our starting ampacity is 55 amps. But we must check for demand factors. Are there more than 3 current carrying conductors? There sure are. So we're going to head to our bundling adjustment factor table. When we get there, we're going to find our range of conductors. Then we're going to cross over to the demand factor. Now, let's just do the math. We take our starting ampacity multiplied by 0.80, and that gives us a new reduced allowable ampacity of 44 amps. Let's get to it. That's the end of lesson 9.5. I want to let you know that you're doing a great job. Keep up the good work. Keep grinding. If you need anything from me, whether it's mentoring, coaching, or any way that I can help you in life or business, you can always just email me at electricalcodecoach@gmail.com or shoot me a call or a text at 423-895-3247. If you don't get me, leave a voicemail and shoot a text. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 9.6 in our video series. In our previous lesson, we learned all about bundling adjustments and how to derate them when wires are bundled inside of a pipe, cable, or raceway. In this lesson, we're going to be learning about ambient temperature corrections. It's very similar. We just pulled from a different table, but it's the same style demand factor process that we've been doing this entire program. Ambient temperature corrections are like this. If wires are run in an extremely hot ambient temperature, it reduces how many amps the wire can handle safely. And let's not forget the basic definition of ampacity. It's how many amps the wire can handle safely under its conditions of use. Let's get to it. Let's take another look at our primary ampacity table. In the last lesson, we learned about the first part of the note that's at the top of the table. And it says that these values are true as long as you don't have more than 3 current carrying conductors. But there's a second piece to this. Now, if you're in the 2017, it's at the top of the table. If you're in the 2020 and the 2023, it's at the bottom of the table. And what it's stating is that these values are true in this table as long as you're in an ambient temperature of 86 degrees Fahrenheit. Anytime you get outside of that ambient temperature, you're going to have to do an ambient temperature correction. Let's imagine that we have this circuit here, black, red, blue, and an equipment grounding conductor. Well, we know from the previous lesson that we will not have to do a bundling adjustment on this one because there's not more than 3 current carrying conductors. But what if we were in a factory who was making a plastic process and they had to have that room at exactly 115 degrees all the time for all of the machines to function properly? That's what we're going to learn about in this lesson when you run into those scenarios and you're pulling circuit conductors. Now let's learn about our temperature corrections table. Go ahead and head to your code cycles table number now. Pause the video if you need to. When we get to the table, we want to verify we're in the right table. And how we do that is make sure that we're in the table that says 86 degrees Fahrenheit. We do not want to be in the table that says 104 degrees Fahrenheit. The table looks identical, but it'll have all the wrong numbers that you need. So you want to make sure that you're in the table that says 86 degrees Fahrenheit. Then if you're able to in your state, I want you to highlight that table. Just highlight the title of it, so when you're flipping through and doing these questions, you're going to know that you're in the right table and you don't have to second guess yourself. Once we know that we're in the right table, let's break down the table. On the left-hand side, we're going to find our column in Celsius. And that's if your actual ambient temperature is in degrees Celsius. You would start on the left-hand side, find the degrees in Celsius, and then finish the process that we're getting ready to learn. Across the top, you'll see a 60, 75, and 90 degree C column. And those correspond with the 60, 75, and 90 degree C columns of our starting ampacity table. Then on the right-hand side, you'll notice degrees Fahrenheit. And that's if your ambient temperature is listed in degrees Fahrenheit. Let me give you an example. Let's imagine that we have this circuit here with our black, red, blue in it. And we have our equipment grounding conductor. Then let's imagine we're in an ambient temperature of 115 degrees Fahrenheit. We would start on the right-hand side, and we would find 115 degrees. Then we would come over to the 90 degree C column, and we would find our correction factor. And all it is another demand factor. And let's imagine that we had a wire that was 50 amps before we started. We found out that it was installed in an ambient temperature of 115 degrees. And we found out that our correction factor was 0.82. All we would have to do is take our starting ampacity, multiply it by 0.82, and we would end up with a new allowable ampacity of 41 amps. Great job! Let's talk about choosing from the right column. Just like with bundling adjustments, 99.9% of the time, we're going to be choosing from the 90 degree C column for our starting ampacity. And then we have to make sure that we choose from the 90 degree C column in our temperature corrections factor table. In the event of it not being listed there, we're likely going to choose from the 75 if it's listed there, but we have to make sure that we choose from the 75 over here as well. But that would be under very rare circumstances when you are in the testing center. But I just want you to know about it just in case. And one thing that I do want to mention at this point in the program is NM cable. NM cable is Romex, and it is actually allowed to be chosen from the 90 degree C column. Romex is just a trade name. They also have Southwire and other trade names. But in the code book, it's called NM cable. And for the purpose of bundling adjustments and temperature corrections, you're allowed to choose from the 90 degree C column when doing those calculations. What is the allowable ampacity of a THHW number 6 copper conductor with an ambient temperature of 142 degrees terminating to 75 degree C terminals? Step 1, we're going to verify that our conductors are listed in the 90 degree C column. We head there and look for THHW, and sure enough, it's right there. Now we're going to find our starting ampacity in the 90 degree C column. We head back to that table. We're going to start over here and find our number 6. Then we're going to cross over and find its ampacity in the 90 degree C. And in this case, it's 75. We're going to take our number 6 at 75. Now we're going to check for demand factors. Is the ambient temperature greater than 86 degrees Fahrenheit? It is, so there will be a demand factor. We're going to head to our respective table depending on our code cycle. And we're going to go find our correction factor. When we get there, we're going to start on the right-hand side because the question stated it in Fahrenheit. Then we're going to go down until we find our range of temperature. Ours was 142 degrees. Then we're going to slide over and find our correction factor. And remember, it's just a demand factor. Now, what we're going to do is we're going to head back and do our math. We take our starting ampacity multiplied by the correction factor, and that gives us a new allowable ampacity of 48.75, and we select B. Great job! What is the allowable ampacity of a number 10 THWN-2 copper conductor that is installed in an area with an ambient temperature of 145 degrees Fahrenheit? Step 1, we're going to verify that our conductors are listed in the 90 degree C column. We head to the table, we look for THWN-2, and sure enough, they're there. Now let's find our starting ampacity in the 90 degree C column. We head back to the table, we come down and find our number 10 on the left, and we cross over to 40 amps. Now we check for demand factors. Is the ambient temperature greater than 86 degrees Fahrenheit? It sure is. We're going to head to our table and find our correction factor. We're going to start on the right-hand side because it's Fahrenheit. We come down and find our range of temperature, which is 145, and we slide over and find our correction factor is 0.65. Now we go back and we take our starting ampacity multiplied by 0.65, and that gives us a new allowable ampacity of 26 amps, and we select D. What is the allowable ampacity of a 2-aught XHHW copper conductor that's installed in an area with an ambient temperature of 68 degrees Celsius? Step 1, we're going to verify that our conductors are listed in the 90 degree C column. When we head to the table, sure enough, they're there. Now let's find our starting ampacity. We're going to go to the table, start on the left-hand side. We're going to find 2-aught copper, then we're going to cross over and find 195 amps. Now we check for demand factors. Is the ambient temperature greater than 30 degrees Celsius? It sure is. So we know that there will be a demand factor. We head to our correction factor table, and in this time we're going to start on the left-hand side because it was listed in degrees Celsius. But we have to be careful to cross all the way back over to the 90 because that's the column that we chose from. And we find that our correction factor is 0.58. We take our starting ampacity, multiply it by the correction factor, and that gives us our new allowable ampacity of 113.1 amps, and we select A. Let's get to it. That's the end of lesson 9.6. You can head over to electricalexamcoach.com for practice questions and different variants of these type of questions. I am the electrical code coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, I hope you're enjoying this live session. I want to take a minute and thank you for joining us and show you a few products that we offer. We offer 400 questions in a digital quiz format for only $39.99. It'll give you the correct answer, the custom feedback, and the code reference when necessary. They're available 100% offline and you only pay one time. Then we have our 20 sets of digital flashcards for only $39.99. They work with you on the go across all your devices, and it's just a one-time fee. But if you really want your license, what I recommend is the Pro version. It comes with all of the videos explaining all the content. Then it comes with the flashcards and the quizzes all built into one. Now we sell two versions. We sell an online version and an offline version. Either one is only $99 each. Let me show you the offline version first. So the offline version comes as a USB. It has all the videos right there in line. Then it has the quizzes built in. And when you scroll down, you're going to see that you have the flashcards all in one set with all 10 lessons, the grind out quizzes, and then topical quizzes that go over specific topics. And each one of those has their own set of flashcards as well. Now, when we get to the online version, it's laid out a little bit different. The online version looks like this. It's more of a program that you work through. Same videos, same quizzes, same flashcards, but it's in a little bit different format. And one unique feature about the online that the offline doesn't have is that, like this question here, there is an actual video of me explaining the answer to that very question. So you do a question, you click feedback, and it has a video of me answering that question. That's something that we weren't able to offer on the USB in the same way. On the offline version, it's just one long video with a bunch of explanations, but it doesn't trigger inside of the custom feedback. It's only digital custom feedback on the offline version because of the limitations. Either way you go, I'm here to help you any way that I can. My bargain is that these videos will help add value to you, and you will in turn add value to others. Let's get to it. Now we're going to learn about sizing motor conductors. 430 is one of the largest articles in the codebook, so I'm only going to show you what you're going to be testing on. When sizing normal motor conductors, you will use the motor FLC and not the FLA nameplate. FLC stands for full load current, and that's a value that we find inside the codebook. The FLA nameplate rating is typically the amperage value that they've stamped on the motor's nameplate. Remember how we've learned previously that every piece of equipment has a nameplate, and it'll say things like what voltage the equipment is and what the amperage is. Well, on motors, they'll typically stamp an amperage, but that's the FLA. So when we're sizing normal motor conductors, we're actually going to use the FLC, and I'm getting ready to teach you how to find that value. We're going to find these values in table 430.248, and that's for single phase. It's on page 321 of the 2017 or page 332 of the 2020. I want you to head there now, pause the video if you need to, and we're getting ready to go over this table. I'll give you a little hint. If you are able to tab your code book, there is a motor FLC tab that will take you right there. So the first thing that we do when we get to this table is we read the black bold heading. It says full load current in amperes for single phase alternating current motors. Great, I feel like we're in the right table. I would go ahead and take a moment, and if you can, and highlight that right there where it says full load current, and then highlight the word single phase. Okay? Highlight the word full load current and single phase. Now, continuing to read the table from top to bottom, left to right, using the black bold headings to navigate the table, we're going to start on the left-hand side. And if you notice there, you have your horsepower. That's going to be whatever the horsepower of the motor is. Now, across the top, all of those black bold headings are respective voltages. Okay? So, what you do is you go to your horsepower, and then you come over and you tee off with whatever voltage your motor or your question states. Okay? So, and one thing I want to note is that these are nominal voltages. So, although it says 115 at the top, it would also include 120. Although all the way at the end across the top of the black bold headings, you could still count 240 in that. These are nominal voltages. Another tip I want to give you is that even if the motor is a single phase motor, but your question states 208 volts, you use whatever column your question states. Don't try to use reasoning and say, well, 208 is only three phase. Whatever your question states, just do it that way. Now let's all head to table 430.250. That's for our three-phase motors. It's on page 322 of the 2017 and on page 333 of the 2020. And when we get there, it's going to be very similar. We always read the black bold heading. It says full load current for three-phase motors. I want you to highlight full load current and three-phase motors if you're allowed to highlight in your state. When we go to read this table, we're going to read it just the same. We start on the left-hand side. It's going to be our respective horsepower. And then coming across the top are our voltages. Again, I want to warn you, make sure that whatever the question states, you choose from that voltage. So even if it doesn't make sense, if they put 230 volts on a three-phase system, just do whatever the question states, okay? Don't try to change the reasoning there because it's very easy to do. So if the question stated a 7.5 horsepower motor on three-phase with 230 volts, you would go over and select an FLC of 22 amps, okay? And if it said a 7.5 horsepower motor for 208 volts, you would go over and tee off and find out that it has an FLC of 24.2 amps, okay? Now let's learn about some more ground rules for motors. You're going to multiply the FLC by 125%, okay? They consider motors continuous duty. Remember how we learned about continuous load and continuous duty previously? Well, it's the same thing. They're assuming that all motors are continuous duty, except, remember this is the National Exception Code, okay? Except when you're dealing with these certain circumstances, okay? For conductors on motors that are under 1200 RPM, that are intermittent duty, multi-speed, or high torque, you're actually going to use the nameplate FLA current rating. And for each one of these, there's going to be individual rules that apply. I'm only going to teach you in our lesson the ones that you're probably going to be tested on. Okay? So, and I'm going to say this over and over in every slide so you don't have to worry about remembering that right now. If it's a normal motor conductor, you're going to multiply the FLC by 125%. If it's any one of these other motors, under 1200 RPM, intermittent duty, multi-speed, or high torque, and your question will say that in there. And I'm going to teach you how to watch for these red flags. You're actually going to use the FLA rating. Why the code book doesn't stick with FLC or FLA only, I don't know, and I wish they would simplify it. Also, one thing I want to note for motor conductors. Remember in the ampacity lesson, we learned that 14 gauge wire can only go on a 15 amp breaker, 12 gauge wire can only go on a 20 amp breaker, and 10 gauge wire can only go on a 30 amp breaker? Well, with motors, these limitations do not apply. Those rules do not apply. So, now that we've set the ground rules, let's get to it. What size copper conductors would you select for a 3 horsepower, 208 volt, 3-phase motor that has an FLA nameplate rating of 9 amps terminating to 75 degree C terminals? One thing I want to note is that they're always going to put that FLA nameplate in there, rating in there to throw you off. So remember, when sizing normal motor conductors, you will use the FLC. For conductors on motors that are under 1200 RPM, intermittent duty, multi-speed, or high torque, you're going to use the nameplate FLA rating. For normal single motor conductors, you're going to multiply that FLC by 125%. So first we go find our FLC. We go to table 430.248 for single phase, and we go to 430.250 for 3-phase. Okay, so when we get to the table, we start on the left-hand side. So we look back at our question. What does it say? It says 3 horsepower. And then it also says 208 volts. So we start at 3 horsepower, we come over and we tee off with 208 volts, and we're going to find that that motor has an FLC of 10.6 amps. Now what we're going to do is take that 10.6 amps, we're going to multiply it by the 125%, 1.25. That's going to give us a new amp draw that we're going to size our wire by of 13.25 amps. Now we head to our primary ampacity table, being sure to select from the 75 degree C column because our terminals are 75 degrees. We're also selecting from a copper conductor. So we start, we go down, and we go on the 75 degree C side of the copper conductors until we find a conductor large enough to cover the known amp load. And in this case, it's 13.25 amps. And we're going to select A, 14 gauge. Great job. What size copper conductors would you select for a 5 horsepower, 208 volt, 3-phase motor that has an FLA nameplate rating of 15.2 amps terminating to 75 degree C terminals? Remember, when sizing normal motor conductors, you will use the FLC. On these types of motors, you're always going to use the FLA. Also, for normal single motor conductors, you're going to multiply that FLC by 125%. First, we need to find our FLC. We're going to head to our respective table. In this case, it's 3-phase, so we're going to go to 430.250. And when we get to 430.250, starting on the left-hand side, we're going to come down and we're going to tee off with our voltage, which is 208 volts, and we're going to find that the motor FLC for this motor is 16.7 amps. Now we take that 16.7 amps, we multiply it by 1.25. That's going to give us a new amperage of 20.875 amps, okay, and we're going to round up to 21. Now we head to our primary ampacity table in the 75 degree C column. We're going to start and we're going to go in the copper side, 75 degree C, and we're going to find a wire that is large enough to cover our known amp load of 21 amps. And we're going to select B. What size copper conductors would you select for a 7.5 horsepower, 208 volt, 3-phase motor that has an FLA nameplate rating of 28.6 amps terminating to 60 degree C terminals? Remember, when sizing normal motor conductors, you're going to use the FLC. If you have one of these specific situations, you're going to use the nameplate FLA. Also, for single motors, we're going to multiply it by the 125%. So we head to our respective table. In this case, it's 3-phase. So we're going to head to 430.250. Starting on the left-hand side, we're going to select our respective horsepower. Then we're going to come down and we're going to tee off with our voltage. Now we're going to select our FLC of 24.2 amps. Now we take that 24.2 amps, we multiply it by 1.25. That's going to give us a new amperage to size our wire by of 30.25. Now we head to our primary ampacity table, being very careful to select from the 60 degree C the 60 degree C column, because our terminals are rated 60 degrees C. And we're going to select C. Great job. What size copper conductors would you select for a 10 horsepower, 115 volt, single phase motor that has an FLA nameplate rating of 95 amps terminating to 75 degrees C terminals? Remember, when sizing normal motor conductors, you're going to use the FLC. When you have these motor situations, you're going to use the nameplate FLA. Also, for normal single motors, you're going to multiply the FLC by 125%. First, we're going to find our FLC. This case, it's single phase, so we're going to go to 430.248. Starting on the left-hand side, we're going to find our respective horsepower. Then we're going to come and tee off with our respective voltage. We're going to find that our FLC is 100 amps. Now we're going to take that 100 amps and we're going to multiply it by 125%. That's going to give us 125 amps. Now we head to our primary ampacity table in the 75° C column. In the copper side, we're going to go down and we're going to select a wire that will cover our known amp draw. In this case, 125 amps. And we're going to select D. Great job. What size copper conductors would you select for a 10 horsepower, 230 volt single phase motor that has an FLA nameplate rating of 47.5 amps, terminating to 75° C terminals? Remember, when sizing normal motor conductors, you're going to use the FLC. In these special conditions, you're going to use the nameplate FLA. Also, for normal single motor conductors, you're going to multiply that FLC by 125%. So first we go to our single phase table of 430.248. Starting on the left-hand side, we're going to choose our respective horsepower. Then we're going to come over and tee off with our voltage. Our FLC is 50 amps. Now we take that FLC, multiply it by 125%. That's going to give us 62.5 amps. Now we head to our primary ampacity table in the 75° C column. And we're going to select a 6-gauge wire. Great job. What size copper conductors would you select for a 10 horsepower, 230 volt single phase motor that has an FLA nameplate rating of 47.5 amps, terminating to 60° C terminals? Remember, when sizing normal motor conductors, we're going to use the FLC. For these motors, we're going to use the FLA. Also, we're going to do that 125% rule. In this case, we're dealing with single phase, so we're going to go to 430.248. Starting on the left-hand side of the table, we're going to come down and find our respective horsepower. Then we're going to come across the top to our respective voltage and tee off. We're going to find that our FLC is 50 amps. Now we're going to take that 50 amps. That's going to give us a new amp draw of 62.5 amps to size our wire by. Now we're going to head to our ampacity table, being sure to select from the 60° C column. In the copper side, in the 60° C column, we go down and we find a wire that will cover our known amp draw. And in this case, we're going to select a number 4. Great job. What size aluminum conductors would you select for a 10 horsepower, 115 volt single phase motor that has an FLA nameplate rating of 95 amps, terminating to 75° C terminals? We're going to use the motor FLC for normal motor conductors. Also, with these motors, we're going to use the FLA. For single motors, we're going to multiply the FLC by 125%. First, we find our FLC. In this case, it's single phase, so we go to 430.248. In that table, we find that we have an FLC of 100 amps. We take 100 multiplied by 1.25. That is going to give us 125 amps. Now we head to our primary ampacity table in the 75° C column, being sure to be on the aluminum side of the table. So we go down on the aluminum side and we find a conductor that will cover our known amp load. And we're going to select C. What size copper conductors would you select for 5 motors with FLCs of 24 amps, 13 amps, 13 amps, 10 amps, 9 amps, terminating to 60° C terminals? Now this one can look like a bear at face value, but once I explain it, it's not very complicated. Everyone head to 430.24. It's on page 303 of the 2017 and on page 314 of the 2020. We're going to go there and do some strategic highlighting. Pause the video now if you need to. Okay, so when we get to 430.24, we're going to read the black gold heading. It says several motors. Okay, so what we're dealing with is when we have more than one motor. I want you to highlight, first off, I want you to highlight in the black bold heading, just highlight the word several motors if you're allowed to highlight in your state, okay? Then go down to part 1 and highlight 125%, and then go down to part 2 and highlight some, and just highlight all of part 2, okay? So you're going to highlight the word 125% in part 1, and you're going to highlight all of part 2. So what this is stating, to simplify it for you, when you're dealing with multiple motors, you take the highest motor. So the highest FLC of all of them. And you multiply that FLC by 125%. Then you just add up all the other motors together and then total them back to the first one that you did the 125% on, and you take that number and go size your wire. Let's practice it on the next slide. All right, so the first thing that we do is we have to select our largest motor. And in this case, it's the 24 amp motor. So we take the largest motor and we multiply it by 125%. That gives us 30 amps. Now all we have to do is total the sum of all the other motors and then add it back to the first motor. So we take the rest of the motors and get that total. And in this case, it's 45. Now here's where we have to be careful to add back that first motor. So we take the 45 of the sum of the other motors, add back the first motor, and that's going to give us 75 amps. Now all we have to do is head to our primary ampacity table, being sure to use the 60° C column. Our conductors that they're asking for are copper. So we go down, what wire's good for 75 amps in the 60° C column? That's right, we're going to select D. Great job. What size copper conductors would you select for 4 motors with FLCs of 22 amps, 20 amps, 14 amps, and 10 amps terminating to 75° C terminals? So the first thing we're going to do is take our largest motor and do the 125%. We take our largest motor, multiply it by 125%, and that gives us 27.5 amps. Now we take all the other motors and add them together. That gives us a total of 44. Now we take and add those two totals together, giving us a total of 71.5 amps. Now we head to our primary ampacity table, and we're going to select on the copper side in the 75° C column a wire that is large enough to cover our known load. And in this case, we're going to select A. Great job. What size copper conductors would you select for a single-phase motor with a nameplate rating of 26 amps that will run a drawbridge for only 5 minutes at a time, terminating to 60° C lugs? So, this is not a normal situation, is it? So that's what you learn to watch out for when sizing motor conductors. Is there anything different going on? And in this case, there is, so we're going to slow down and figure it out. Everyone head to 430.22e. It's on page 302 of the 2017 and on page 313 of the 2020. There are provisions in the code book for when motors will only run for fixed or limited amount of times that you can have a reduced amp draw to size your wire by. Or sometimes it's actually an increased amp draw. So it's just really another demand factor. So everybody head there now. Pause the video now if you need to. So when we get to 430.22e, we're going to read the black bold heading. It says for other than continuous duty motors. Remember, all of our other motors, we did the 1.25 because it was a continuous duty. But what if they're not continuous duty? And that's what we're going to cover here. It lets us know that conductors for motors that are used short time, intermittent, periodic, or varying duty shall have an ampacity of not less than the percentages that are listed, okay, in 430.22e. Okay, so these ones we are going to go to 430.22e, and it's a table. It's usually on the next page of your code book. So whether you're in the 2017 or the 2020, it's typically in the next page over. When we get to table 430.22e, let's look at it now, starting with the black bold heading. It says duty cycle service. Pretty sweet. Now using our black bold headings, top to bottom, left to right. Starting on the left-hand side is going to be our classification of service. Okay, so on the left-hand side, we're going to pick whatever scenario our question lists. And if you look down through there, somewhere you're going to find something about a drawbridge, okay, or whatever your question states. Then going across the top in the black bold headings, you're going to see 5-minute, 15-minute, 30 to 6-minute, or continuous duty rated. So with that being said, what you're going to do is start on the left-hand side and find your situation, then come across the top and tee off with your amount of time. So what you will do is, when you get that value, it's just going to be another multiplier. It's just another demand factor. So let's look at the first one. In a 5-minute rated motor for short-time duty operating valves. That's the first one you come to on the left-hand side. If you go over to a 5-minute motor, it's 110%. So all you do is take and multiply it by 1.10. It's just another demand factor. All right, so let's look at our question again and answer it. So in this case, we have a 26 amp draw. Remember, we don't use the FLCs on this type of question. You're going to use the nameplate rating. And we're going to have a drawbridge for 5 minutes. So we go to our table, 430.22e, starting on the left-hand side, and let's find something until it says the word drawbridge. Looking down, And if you look right there, in the middle section, it says drawbridges. Now we need to come over and tee off with our respective time. In this case, it's 5 minutes. So we find what type our motor is, then we slide over to our time limit, and we're going to find our multiplier, and we're going to take our amperage and multiply it by that demand factor. In this case, it's 85%. So we take our nameplate rating, multiplied it by 0.85, and that's going to give us 22.1 amps. Now we can head to our ampacity table and size a wire that can hold 22 point, like from the 60 degree C column. So when we get there, we come on the copper side, 60 degree C, and let's find a wire that can cover our known load. And in this case, we're going to select C. Great job. What size copper conductors would you select for a 3-phase motor with a nameplate rating of 40 amps running some short time duty operating valves that will only run for 15-minute intervals terminating to 75 degree C lugs? One thing I want to note is that if you watched our video back in week 1 that teaches you how to make your own tabs, you should have made a tab for this table, okay? This is one of the tabs that we highly recommend making that are not in the Mike Holt tabs that we sell. So with that being said, you can use your tab for even faster reference to this table. So we see that there's something going on here, and we recognize that it's a duty cycle question. We're going to head to our demand factor table for duty cycles. It's 430.22e. Then starting on the left-hand side, we're going to look for our situation. In this case, it's short time duty operating valves. So when we find it, we come over and we tee off with our time, which is 15 minutes, and we're going to find a demand factor of 120%. Then we take our original 40 amps, multiply it by 1.20. Now we have 48 amps. Let's head to our ampacity table. Let's find a wire that will hold 48 amps in the 75 degree C of the copper side. And in this case, we're going to select D. Great job. Now we're going to learn about motor short circuit ground fault protection. There are 2 types of protection for a motor. One of them is called short circuit ground fault protection, and the other one is called overload protection. They are 2 separate things, and they've named them on purpose so you would know what rules to apply. So let's learn about what they both are, and that way we can rightly divide them. And all I want you to think about, so you don't overcomplicate it, is both of these protections are just breakers and fuses. Okay? And that is was so hard for me to understand at the beginning, is that because you hear these 2 different types of protection and you can really get lost in the sauce. But all they are breakers and fuses. And I'm going to explain how a basic short circuit ground fault protection and motor overload setup would work now. Okay, so we have both the types of protection. Let's imagine that this is a motor. Next to the motor, there's a disconnect. And then feeding that disconnect, there's a panel. Okay, at the original panel is where you're going to put your short circuit ground fault protection. At the disconnect is where you're going to put your motor overload protection. The first protection, the short circuit ground fault protection, what do you think it protects against? That's right, short circuits and ground faults. Okay? The second protection, the motor overload protection, does exactly what it sounds like. It protects against overloads of the motors. And what that does is protects the motor windings, and the wire going from the disconnect to the motor. It's size smaller than the first protection. The first protection is if there is a true short circuit or a true ground fault. It's going to trip the breaker. That short circuit ground fault protection is always going to be a little bit larger on that motor, and that's going to allow for the inrush of current. The motor overload protection is going to be a little bit smaller, sometimes a lot smaller, and the reason is that is going to protect the internal parts of the motor. We don't want the motor itself burning up. Now let's learn how to size it. What size short circuit ground fault protection would you select for a 5 horsepower, 208 volt AC 3-phase motor terminating to 60 degree C terminals with a nameplate FLA rating of 26 amps using an inverse time breaker? You will never size short circuit ground fault protection from the nameplate or FLA rating. I will say this one time, that if the FLC is printed on the nameplate, you can use it, but it has to say FLC, okay? FLC, it's got to say full load current. You could use it if it happened to be there. But what we're going to do is like we normally do to find our FLC, and we're going to head to our FLC tables. So let's flip to our FLC tab. Using table 430.250 because it's a 3-phase motor, what is our FLC? We start on the left-hand side for our horsepower. Then we come off and T with our voltage, and we're going to select our FLC. In this case, it's 16.7 amps. Now we have to go check out a new table. Okay, so everyone head to 430.52, page 308 in the 2017, and page 319 in the 2020. When we get there, the first thing that we do is we read our black bold heading. It says maximum rating or setting for motor, branch circuit, short circuit, ground fault protective devices. I feel like we're in the right place. Now on the left-hand side is going to be your type of motor, whether single phase or polyphase. Then across the top, you're going to notice different type of devices. There's a non-time delay fuse, a dual element fuse, an instantaneous trip breaker, and an inverse time breaker, which is the breakers that we normally use. So let's go ahead and answer our question. First, we find our motor in the motor column. We go down to polyphase. I want to let you know that that just means three-phase. Now we come over and tee off with our type device. In this question, it was an inverse time breaker. Now what we do is we take that multiplier and do the math. We take our FLC, which is 16.7, we multiply it by 2.50. That is going to give us a new amperage to size our breaker by of 41.75. All right, so we took and we did our math. Now, do they make a 41.75 amp breaker? And the answer is no. I want you guys to know that with motor short circuit ground fault protection, you can use the next size up standard breaker. When we get to motor overload protection, you cannot. So with short circuit ground fault protection, you can use the next size up breaker. So we head to table 240.6a and we check and we find a breaker that is the next size up from 41.75 amps. And in this case, it's going to be B. What size short circuit ground fault protective device would you select for a 7.5 horsepower, 115 volt AC single phase motor terminating to 75 degree C terminals with a nameplate FLA rating of 71 amps using a dual element fuse? Now, we never size short circuit ground fault protective from the nameplate or FLA rating. We're going to use the FLC. So we go and we find out what our FLC is. Now we head to table 430.248. What is our FLC? We start on the left-hand side, find our horsepower, come across to our voltage, and we're going to find that our FLC is 80 amps. Now we head to 430.52 and find our multiplier. Starting on the left-hand side and finding our motor, we come over and we tee off with our type of device. Then we're going to find that it's 175% for dual element fuses. Remember, this is just another demand factor. So we take 80 multiplied by 1.75. That's going to give us 140 amps. Now we head over to 240.6a and select the next size up. And in this case, it's going to be B. What size motor short circuit ground fault protective device would you select for a 7.5 horsepower, 208 volt, three-phase motor terminating to 60 degree C terminals with a nameplate FLA rating of 26 amps using a dual element fuse? We will never size short circuit ground fault protection from the nameplate or FLA rating. First thing we do is we find our FLC. Now we head to table 430.250. What is our FLC? Starting on the left with horsepower, coming over to the voltage, we find that our FLC is 24.2 amps. Now we head to table 430.250 and find our multiplier. Starting on the left for polyphase and then coming over to our type of device, we're going to find that it's 175%. We take our FLC, multiply by 1.75. That's going to give us 42.35. Now we head to table 240.6a and select the next size up. And we select B. What size short circuit ground fault protection would you select for a 5 horsepower, 115 volt AC single phase motor terminating to 75 degree C terminals with a nameplate FLA rating of 60 amps using an instantaneous trip breaker? And I love this one here. You're going to think it's hilarious. So we never size normal short circuit ground fault protection from the nameplate or FLA rating. First thing that we do is find out what our FLC is. We head to table 430.248. What is our FLC? Starting on the left-hand side with our horsepower, coming across to our voltage, we're going to find that the FLC is 56 amps. Now we head to table 430.52 and find our multiplier, starting on the left-hand side, finding single phase, then coming across to the type of device. In this case, we're going to find that our multiplier is 800%. So we take our FLC, we multiply it by 800. And we take 56 multiplied by 8, and that's going to give us 448 amps to size our device by. Now we're going to head to table 240.6a. We're going to select the next size up, and we're going to select a 450 amp overcurrent device. Now, just for fun, we're going to take this same question and we're going to size the conductors. Okay.